Back, everyone, to week 5 of iTech 770 Health Information Technology Databases. This week marks an important transition in our journey with SQL. We've spent the last few weeks learning how to create database structures and retrieve them. Now we're going to learn how to actually modify the data that lives inside these structures. This is part 5A, and we're focusing on data manipulation language, or DML, which consists of 3 essential commands: insert, update, and delete. These are the commands you'll use every single day when working with healthcare databases, whether you're registering a new patient, updating a diagnosis, or archiving old records. Now, let me give you the roadmap for this week, because it's a packed week with 4 distinct parts. And in 5A now, we'll cover the DML operations. Part B will teach you the join operations, which is how we combine data from multiple tables together. The third part, 5C, shifts gears to cover interoperability and electronic health record EHR vendors, giving you the industry context you need to understand how these databases fit into the broader healthcare landscape. Then finally, part 4, 5D, brings everything together with a deep dive into the US CDI, the United States Core Data for Interoperability Standard. Notice how part 5A is highlighted here, because that's our current focus. And by the end of this whole week, you'll have both the technical SQL skills and the healthcare industry knowledge to understand how data flows through modern healthcare information systems. But before we dive into this new material, let's anchor ourselves and see what we learned last week. In week 4, we covered DDL, which stands for Data Definition Language. DDL is all about creating structure. We used create to build the tables, and alter to modify them, and drop to remove them. We also spent significant time on select statements, learning how to retrieve data using the where clause and order by to sort. Think of it this way, simplistically. DDL is like building a filing cabinet. You're constructing the drawers, the dividers, the labels. Select is like reading the papers that are already filed. Well, what about actually putting papers into the cabinet? What about updating information on those papers or removing outdated documents? That's exactly what we're doing now with data manipulation language. Today we learn how to file papers, update them, and remove them from the database filing cabinet. So here's the big picture. We have data definition language, DDL, for defining the structure. DML, data manipulation language, for manipulating the data. And we also have DQL for querying data, DCL for controlling access through permissions, and TCL for transaction control. But today, our focus is squarely on the second row on this slide, the data manipulation language, the insert, update, and delete clauses. These are our magic commands. They allow us to change what's stored in our database. Every other category either builds the container, reads from it, or controls who can access it, or manages how changes are grouped together. But data manipulation language is where the actual data modification happens. In healthcare, these 3 commands represent real clinical and administrative actions: registering patients, recording diagnoses, updating medications, correcting errors, and managing records throughout their life cycles. Let's make this concrete with a healthcare example. For example, insert is what happens when a new patient walks through the door at the registration desk. It's also what happens when a lab result comes back from the analyzers. It's what happens when a provider schedules a new appointment. You're adding new records, new rows to the database. Now, update is what happens when a patient moves and you need to change their address. It's also what happens when a provider adjusts a medication dosage. It's what happens when an encounter status changes from in progress to completed. You're modifying existing records. And delete is what happens when you need to remove a duplicate record or one that was entered by mistake. It's what happens when an appointment is canceled, or it can happen during archival processes. Now here's the critical point I want you to remember throughout this entire lecture. In healthcare, every single data manipulation language operation is a potential auditable event. HIPAA requires that we maintain audit trails of who accessed what data and when. So this means every insert, update, and delete you execute in a production environment healthcare system is being logged somewhere. This isn't just about the technical correctness, it's about regulatory compliance and patient safety. Well, let's start at the beginning. We have three different statement types. The first one we're going to talk about is insert. This is the command to add new rows, to add new records. The basic syntax is very straightforward. Insert into. Then you specify the table name, then a list of the columns in parentheses, then the values to insert into those columns, followed by the actual values you want to insert. Also, they're in parentheses. Notice that I'm explicitly listing the columns. This is best practice, but it's not a requirement. You could technically omit the column list and just provide a comma delimited list of values so long as you had a value for every column in the table in the proper order. But I strongly advise against that approach. Why? Because if someone adds a new column to the table later, your insert statement structure won't work. It will break. So by explicitly naming your columns, your code is sort of self-documenting and far easier to maintain. The values you provide must match the columns in both order and the data type. So if you list first name, then last name, then date of birth, your values must be in that exact same sequence. So when the insert succeeds, the database will tell you how many rows were inserted. Like typically a insert 01 means 0 rows existed before and now 1 exists after your insert command. Well, here's a real example using our X-Health database example. We're inserting a new patient named Maria Garcia. Notice the structure. We specify exactly which columns we're populating, which are first name, last name, date of birth, gender, and phone. Then we provide the corresponding values. Text values like names are enclosed in single quotes. The date is also in single quotes and follows the ISO, International Standards Organization's format with year, month, and date. We'll talk later about alternative formats for dates. Then gender is a single character. It's a text field, also in quotes. Phone number is stored as text because it might contain dashes or parentheses. What about the patient ID? In our X-Health schema, patient ID is defined as serial. What does that mean? It means that the database, Postgres, automatically generates the next sequential ID automatically for us. So we don't need to provide it. What about columns we didn't mention, like address or email? Those will be initially set to null, assuming those columns are allowed to have null values. If you don't specify a value in a column and it has not null specified, then the insert will fail. Now, what about multiple rows? You're not limited to inserting just one row at a time. Here we're adding 3 patients with a single insert statement. After the values keyword, we have 3 sets of parentheses, each containing 1 patient's data, separated again by commas. That's your delimiter. This is significantly more efficient than running 3 separate insert statements. Now, you can clearly see that writing the statements as 3 separate insert statements would get the same final result, But when you're in production and doing lots of data entry, you want it to be as efficient as possible. So each SQL statement has some associated overhead. The database has to parse it, create an execution plan, execute it, and return the result. When you batch multiple rows into one statement, you only incur that overhead once. And there's another important concept here, atomicity. When you insert multiple rows in a single statement, remember this, either all of them succeed or none of them do. If the third row violates a constraint, the first two rows won't be inserted either. The entire operation will be rolled back. And this is actually a feature. This is a designed-in feature for Postgres. It's not a bug. It ensures that your data remains consistent. You won't end up with a partial insert where some records made it and others didn't. All right, let's walk you back through the most common insert scenarios you'll encounter in our healthcare databases. Patient registration creates a new record in the patients table with identifying information like patient ID, name, date of birth, insurance details. When a patient visits a provider, we create a new encounter record, linking the patient to the provider with a date, visit type. Also, when lab results come back, we insert into the lab results table with the patient reference, the LOINC code identifying what test was done, and the actual result values. When a provider writes a prescription, we insert a row, into the medications table with columns such as the patient, the NDC code identifying the drug, and dosage instructions. When a diagnosis is made during an encounter, we insert that into the diagnosis table, linking it to the encounter with the ICD-10 code. And notice how each insert connects to other tables through foreign keys, an important concept. The patient ID in encounters references the patient's table. The encounter ID in the diagnosis references the encounters table. This is how relational databases have their power. This is relational database in action. All right, common errors. What can go wrong? The most common error is a primary key violation. If you try to insert a patient ID that already exists, the database will automatically reject it. The solution is either let the database automatically generate patient IDs using the serial constraint, or to check carefully that the ID is correct before you try to access a record. The next common error is the not null violation. If you try to insert a record without providing a value for a required column, the insert will fail. The solution is simple. Make sure you provide values for all the required fields. Foreign key violations occur when you try to reference a record that doesn't exist. For example, if you try to create an encounter for patient ID 9999, but that patient doesn't exist in the patients table, the database will automatically reject it. So always ensure patient records exist before creating child records. And finally, data type mismatches happen when you provide the wrong data type. Putting text in a numeric field or an invalid date format will cause errors. So the solution is to validate your data before attempting the insert and ensure your data types match the schema. Now let's move to the update, the command for modifying existing records. The syntax is straightforward, has three parts. The update keyword, then specify which table. The set specifies which columns to change and their new values, and where specifies which rows to modify. The set clause can update one or multiple columns separated by commas. You specify the column name, an equals sign, and the new value. Now I need to deliver the most important warning of this entire lecture, and I want you to burn this into your memory. The where clause is not optional in real practice. Technically, the database will let you run an update without a where clause, but if you do that, you will update every single row in the entire table. I've seen careers damaged and systems taken offline because someone ran an update without the where clause in a production environment. In healthcare, this could mean changing every patient's status, like to inactive, or overwriting every diagnosis code, or corrupting every medication record. Always, always include a where clause unless you have a very specific and intentional reason to update all the rows. That's very, very rare. Let me show you exactly what I mean by a side-by-side comparison. On the left, we have a dangerous update statement. Update patient set status equal inactive with a semicolon. That means that's the end of that statement. That's a dangerous update statement. It sets a status inactive for the entire patient's table because it doesn't have a where clause. The moment you execute this, every single patient in your database becomes inactive. If you have 50,000 patients, they're all now marked inactive. Your clinic can't see any of these patients. Appointments can't be scheduled. Clinical workflows grind to a halt. This is a production outage caused by a missing where clause. Now on the right side, however, we have the safe version. It's almost identical, except it has its where clause. Like for where the patient ID equals 501 means it's just going to get that one row. Everyone else remains unchanged. So the difference between a catastrophic data corruption event and a routine database update is literally one line of code. So make this your mantra. Before executing any update statement, check for the where clause. Check again. In a production environment especially, I recommend writing your where clause first before you even write the set clause. That way you can never accidentally run an unfiltered update. Here's a single column example, a very straightforward example, updating a patient's phone number. We specify the patient's table, set the phone column to the new value, and use where to target only patient 501. When this executes successfully, Postgres returns update 1, indicating one row was affected. If it said update 0, that would mean no rows were modified, that no rows matched your where clause, so nothing changed. If it says update 500 when you expect it to update just one patient, that would mean that would give you a red flag, meaning that your where clause wasn't specific enough and multiple records were modified. Always check that row count on return to be sure that it matches your expectations. Update multiple columns. When a patient moves, you typically need to update multiple columns at once. So here we're updating the address, city, zip code, and updated at, all in a single statement. Each column assignment is separated by commas within the set clause. Notice that the last column, updated at, equals current timestamp. This is a crucial best practice for healthcare databases. By setting the updated at timestamp every time you modify a record, you maintain an audit trail of when changes occurred. Many healthcare systems require this for compliance purposes. So if someone asks, when was the patient's address last changed, you can answer that question directly from the database. And some systems even go further and include an updated by column to track who made that change. If your schema includes audit columns like these, try to remember to update them along with your data changes. Here's a reference table of common update scenarios that you will encounter. Address changes. Update the patient's table with new location information plus the timestamp. Insurance updates modify policy information when a patient coverage might change. Encounter status updates are extremely common, tracking a visit from scheduled to when the patient arrives, to in progress, to completed. So there are multiple changes occurring even in the same day for the same row. Lab result corrections happen when an initial result needs to be amended, and you should update the value along with the correction metadata showing when and why it was updated. Also, medication dose changes modify the dosage instructions when the provider adjusts the prescription. But each of these represents a real clinical or administrative workflow, and each one requires careful attention to the where clause to ensure you're updating only the intended record. Update statements can do even more than just update static values. They can perform calculations. In this example, we're adding 30 to the existing quantity value. The syntax quantity equals quantity plus 30 tells the database to take the current value, add 30 to it, and then store that result. Now this is useful in inventory adjustments, or refill counts, or running totals, similar scenarios. Notice we also have multiple conditions in the where clause, and combined with an and, the row must have refills remaining greater than 0 and belong to patient 501. Both conditions must be true in this case for the row to be updated. You can build complex where clauses using and or and parentheses for grouping. You can use comparison operators, the like statement, for pattern matching. You can use the in for specifying a list of possible match values. And the key is to be precise enough that you update exactly the records you intend to and nothing else. All right, now to the delete statement, the command for removing records. The syntax is deceptively simple. Delete from, specify the table, where, you give the condition that for the record you want to delete, and that's it. There's no column specification because when you delete a row, all columns are deleted. If you want to clear a single column's value, what do? You use the update command, not the delete, and you set the specific column to null. Don't use the delete command. The same critical warning applies here as with update. Without a where clause, delete removes every row in the table. The table structure remains. It's still there with all its columns and constraints, but it's completely empty. You've got an empty filing cabinet. Every record is gone in an instant. In healthcare, this could mean losing all the patient records, all the clinical history, all the appointment data. This is why database administrators configure extensive backup systems and why production access is tightly controlled. A single delete statement without the where clause can undo years and years of data entry. Let me illustrate with another side-by-side comparison. On the left side of this example, it says delete from appointments with no where clause. So what's going to happen? Your appointments table is now empty. Every scheduled visit, every completed encounter, every canceled appointment, they're all gone. Your scheduling system knows nothing anymore. Patients can't check their upcoming visits. Providers can't see their schedules. Now look at the safe side on the right in the green. We have a targeted delete. We're removing a specific appointment identified by an appointment ID 1001, and we've added a second condition requiring the status to be canceled. Both conditions must be true. And this is what I call a defensive programming philosophy. We're adding all the necessary conditions to your where clause to be extra safe. If you accidentally type the wrong appointment ID, the record won't be deleted unless it's also been canceled. Think of the additional where conditions as guardrails, protecting you from making mistakes. Let's look at some examples of how delete is used in real life. Something we want to do very carefully. Let's say an appointment is canceled. Should you delete the record, or should you update its status to canceled? In most healthcare systems, you update rather than delete, because you want to maintain a history of canceled appointments for reporting purposes and other analyses. Removing duplicates is a legitimate cause for a delete, but you need to first carefully identify which of the records, if you have duplicates, is the correct one to keep and which one to delete. Patient record removal is complicated by the HIPAA regulations and retention requirements. Healthcare organizations are legally required to retain medical records for specific periods, often 7 years or longer, depending on the state. You just can't delete patient data because someone asks you to, or because you think the data is old. Archiving old data often involves moving records to archive tables rather than deleting them. Now, test data cleanup is appropriate only after verifying that you're in a test environment, not anywhere near the production environment. So the common theme here is that delete is rarely the right choice in healthcare. Usually you want to preserve data for compliance, audit, and analytical purposes. Delete versus soft delete, a very important concept. A hard delete is an actual delete command, the delete statement, that removes the row from the table permanently. Once it's gone, unless you have a backup. A soft delete uses an update to mark a record as inactive while still maintaining and keeping all the data intact. We set isActive to false and record when the deletion occurred in deleted at. Why is soft delete preferred in healthcare? Well, there's 3 main reasons. First, for audit trail purposes. Regulators and auditors may need to see what data existed at some time in the past. With soft delete, you can always show what was there and when it was marked to be deleted. Second, HIPAA compliance. As mentioned earlier, healthcare records must be retained for specific periods. So soft delete lets you hide records from normal application queries while maintaining them for compliance purposes. And third, data recovery. People make mistakes. With soft delete, if someone accidentally marks the wrong patient as inactive, you can easily restore the patient by setting isActive back to true. But with a hard delete, you're going to have to go to your backup archival files and try to find the record and copy it back to the active file. It's a much more complex process, fraught with errors. So for your applications, add where isActive equals true to your select queries so inactive records are filtered out. Users don't see them, but they're still there for the rare circumstances which you might need them. All right, foreign key constraints and delete. Let's talk about those. Even when you want to hard delete a record, the database may stop you because of foreign key constraints. Think about this very carefully. Let's look at this example. We're trying to delete patient 501, but the database throws an error because that patient has had encounters. The encounters table has a foreign key referencing the patient's table. So if we deleted the patient, those encounters would now be orphaned, pointing to a patient that no longer exists. The database system, Postgres, protects against this referential integrity violation by preventing this. You have 3 options. First, delete the child records first, like the encounters. Delete all the encounters for patient 501 and then delete the patient. But those encounters might have their own children, like diagnoses and medications and procedures or lab results. So you'd have to delete all those first before you can delete the encounter. So this cascades through your entire database schema. Secondly, you can use cascade. What does cascade mean? We talked about that briefly before. If you use a cascade clause in your delete, it will automatically delete the dependent rows from the other tables where foreign keys exist. But this is a very complex process, and it's a little bit dangerous to let the system do this automatically for you. It's better to do it explicitly in your code to be sure that your delete is clean. This is a very dangerous process to use the cascade, because you could inadvertently delete years of medical history with a single powerful command. So I recommend against using cascade in production healthcare systems. And third, this is my recommendation. Use soft delete instead. Mark the patient as inactive. Their records remain intact for your compliance purposes, but they're hidden from normal operations by just using a test to say is active. This is the safest approach for healthcare databases. What about data manipulation language and transactions? Let's talk about transactions, which are how databases ensure data integrity across multiple operations. A transaction is a group of statements that succeed or fail as a unit. You start with begin, execute your statement, and then end with either a commit to save all the changes you just made or a rollback to undo everything. In this example, we're creating a new encounter with associated diagnoses and procedures, and these records are related. They represent a single clinical event. If the diagnosis insert fails for some reason, we don't want the encounter record to exist without its diagnoses. That would be inconsistent data. So by wrapping everything in a transaction with the begin structure, we guarantee atomicity. Either all three inserts succeed and the complete clinical event is recorded, or none of them succeed and the database remains unchanged. The acronym ACID describes the properties of database transactions. Atomicity means all or nothing, as we just discussed. So that's the atomicity. Consistency means the database moves from one valid state to another. Isolation means concurrent transactions don't interfere with each other. And durability means once committed, the data survives system failures. These properties are essential for healthcare systems where the integrity of the data is critical and impacts patient safety. Let's work through a complete patient registration workflow using our example of the xHealth database. So what is step one? Step one is inserting the new patient, usually happening at registration. Let's add Emily Johnson with her date of birth to the patients table. Notice we're not providing a patient ID in this statement. Why is that? Because our schema used serial for the patient ID column, and that means it automatically generates the ID number serially, sequentially. In a real system, this insert would return the generated ID, and we'd capture that for use in subsequent statements. Step two creates the initial encounter. This links the new patient to a provider for their first visit. In practice, you'd use the patient ID returned from that first insert rather than hard coding 501. The encounter date is set to today's date, and we reference the provider who will see that patient. This two-step workflow represents what happens dozens or hundreds of times every day in a healthcare facility. Patient walks in, registration desk creates the patient record, creates the encounter for the visit today, and the data flows from the real world into your database through a series of insert statements. Here's a lab result workflow showing both insert and update. First, we insert the new lab result. The patient ID links who the lab result belongs to. The LOINC code 2339-0 identifies this as a glucose test. The result value, result unit, and result date complete that record. What happens when the lab calls back to say there was a calibration issue and the value should have been 96.0 instead of 95.5? Well, then we use that update to correct it. We target the specific result using multiple where conditions to be sure we get the proper row. The patient ID, the LOINC code together identify the proper row, the proper record we want to update. In a production system, you'd like to use the lab result ID for more precise targeting, and you'd also record who made the correction and why. Lab corrections are significant events that may require additional documentation for regulatory compliance. Some systems create an entirely new record and mark the original as superseded rather than modifying it in place. And the approach depends on your organization's policies and sometimes regulatory requirements. All right, this scenario demonstrates the complete lifecycle of an appointment using insert, update, and delete. First, we insert a new appointment. The patient is scheduled to see the provider 1 on February 15th at 9 a.m. with a status of scheduled. Then the patient calls to cancel. Well, rather than deleting the appointment, we update it. We set status to canceled and record when the cancellation occurred in the canceled at column. This preserves the appointment history. We can later analyze cancellation patterns, no-show rates, and scheduling efficiency because we kept the original data. Finally, for database maintenance, we might periodically delete canceled appointments that, for example, are like more than a year old. This cleanup query uses a compound where clause. The status must be canceled and the cancellation must have occurred more than a year ago. We're not deleting recent cancellations that might still be relevant for operational purposes. This is an example of a legitimate, targeted delete that removes truly obsolete data while preserving all the recent medical history. All right, let's summarize the key best practices that we've discussed. We always use where clauses with the update and delete. Can't emphasize this enough. A missing where clause is the most common cause of catastrophic data modification. Use transactions when multiple related changes need to succeed or fail together. This maintains data integrity and reflects real-world events that span multiple tables. Prefer soft delete over hard delete. In healthcare, data retention requirements and audit needs mean you must always want to keep records even when they're no longer active. So update timestamps every time you modify a record. This creates an audit trail showing when changes occurred. Include an updated by column to track who made the changes, supporting better accountability and the ability to investigate when some questions might arise at a later date. And finally, never experiment in your production data. Always test your data manipulation language statements in a development test environment. When you execute in production, start with select using the same where clause to verify which rows will be affected. Only after confirming the scope should you run the actual update or especially a delete. So common mistakes. What are the common mistakes we've discussed? Let's review them. The ones that I see most often and how you might avoid them. Well, the first is forgetting the where clause. That's an egregious error you certainly don't want to make. Prevention requires code review processes and using transactions so you can roll back mistakes before performing a commit. Wrong data types. This is another common error. They cause insert failures. Validate your input data before attempting to do the database operation. Third, ignoring constraints. That can lead to referential integrity errors. Postgres won't allow that. You have to have your foreign keys intact in order to create the data. So prevention means understanding your schema's relationships and ensuring patient records exist before creating children. Failing to back up before delete operations means data loss could be permanent. So always back up, or at a minimum, use transactions when performing deletes. Hard coding IDs like patient ID equals 501 works in development, but breaks down when you move to production where IDs are different. Use variables, parameters, or lookups instead of hard code values like a 501. It should be something that comes from another source. So each of these mistakes represents real incidents that I've seen or had to clean up after. Try to learn from others' errors so we don't repeat them. As your databases grow larger, performance becomes increasingly important. So batch inserts that combine multiple rows into a single statement are significantly faster than running individual insert statements. The overhead of parsing and planning each statement can add up substantially. Update operations are fast when there's an index on the columns used in your where clause. Now this is something we haven't discussed before about the existence or non-existence of indexes in keys. But we'll talk about that more later. But the columns that have keys that are indexed can be much more rapidly perused. So if you're filtering something by patient ID, make sure that patient ID is an indexed column. Without an index, the database must scan every row to find those matches. Also, when deleting large data sets, do it in chunks rather than all at once. A delete that affects millions of rows will lock that database, that table up for a long time, blocking any other access. So instead, delete in batches of 1,000, 10,000, 100,000 rows with short pauses between so people can get production work done. Also, after large delete operations in Postgres, you can run a vacuum statement to reclaim the disk space. Deleted rows aren't immediately removed from the disk, but the vacuum statement will actually clean them up. And finally, remember that indexes speed up select and update with where, but slow down insert and delete because they have to recalculate the indexes after each entry. So each index must be maintained when the data changes. So there's a trade-off between read performance and write performance when you have columns that are indexed. All right, let's summarize what we're doing in 5A today here. Bring it all together. What does insert do? It adds new rows to your table. Your key concern is checking constraints first. Make sure you're providing required values for all the columns using valid foreign keys and not duplicating any primary keys. Update modifies existing rows. Your key concern is always using a where clause to target the specific records you want to update. And then delete. It removes rows, and your key concern in healthcare is preferring soft delete to maintain audit trails and complying with any regulatory retention requirements. So the healthcare context infuses everything we've discussed. Every data manipulation language operation is a potential audit event that may be logged and reviewed. Transactions ensure data integrity when clinical events span multiple tables. Soft deletes preserve compliance records that regulators may request even years later. These aren't just technical best practices, they're operational necessities in a highly regulated environment such as healthcare. All right, so what's going to happen next? The second part of week 5. Let's look ahead. Then we're going to learn join operations. What is a join operation? Well, this is the SQL feature that lets us combine data from multiple tables into a single cohesive entity, a single query. So far, we've worked with one table at a time. But real questions often require access to data from multiple places at the same time, simultaneously. Like, which patients seen by Dr. Smith have diabetes? Well, that requires joining patients to encounters to providers to diagnoses. All tables have to be interconnected. What lab results are abnormal for patients over age 65? A question like that requires joining patients to lab results with age calculations. A very sophisticated query, but it can be done, but you have to have the join. We're going to cover several different types of joins. As you can see on the slide, there are 4 common kinds of joins. There's inner join, left join, right join, and full outer joins. And we will be discussing them next. Full outer join, well, let's briefly talk about what they do. The inner join returns only records that match from both tables. An inner join means if you're trying to join 2 tables, if there's a match on both tables, then that record will transfer into your results. The left join returns all records from the first table plus the matches from the second table. So your final result will have fewer rows than you started with if you added the 2 tables together. Now the right join is just the opposite. It only joins the records on the rows on the left side if there's a corresponding record on the right side. The full outer join returns everything from both tables, so this can end up with a lot of records. We'll practice writing healthcare queries that connect patients to encounters to diagnosis to labs, building very complex queries, ones that you'll use on a daily basis in your clinical and administrative career. So I will see you then.